Hello and welcome back to Real Analysis. And first I want to thank all the nice supporters on Steady and PayPal. Now in today's part 52 we will talk about examples for the Riemann integral. For this, let's quickly recall the definition for Riemann integrable functions. What we need is a bounded function defined on the compact interval AB. And we call this function Riemann integrable if the upper and the lower integral are the same. There, the lower integral is given when we approximate the integral with step functions from below, and the upper integral is given when we approximate the integral by step functions from above. Hence, we only get one well-defined value here, which we call the integral of the function f. Now I can tell you, it's possible to rewrite this definition here without using supremum and infimum. In this alternative form, you might recognize the approximation in a better way. To get the idea, let's simply draw a small graph here. So you see, our mission is that we approximate this area here from above and from below. Now let's say this here is a step function phi, and you see it's an approximation from below. Also, then you can see without a problem and even with the same partition of the x-axis, we can choose a step function phi that approximates the integral from above. However, the important thing I want to show you here is that the area between both step functions is very small. Even better, we can make it as small as we want. And exactly this fact is what we can use for an equivalent formulation here. Namely, for all epsilon greater than 0, we find step functions phi and psi with the property that the one lies below f and the other one above f. And moreover, we have that the difference between both integrals here is less than the given epsilon. Here, please note, we know that the integral of psi is always bigger than the integral of phi. So we don't need an absolute value here, we can just calculate the difference. Okay, now this description here makes it a little bit easier for us to look at examples. Therefore, I would say let's start with the first one now. And I would like to start with a counterexample. It's the so-called Dirichlet function. Indeed, it sounds more complicated than it really is, and I would say let's define the function on the interval 0, 1. And now the common definition of the function just considers two cases. We either get the value 1 or 0, depending if the x we put in is rational or not. By using the set names, we can say it's 1 when x comes from Q, and it's 0 when x comes not from Q. Now, at first glance, this looks like a very simple function, so let's draw the graph for it. And there, you should immediately see we have infinitely many rational points for the value 1, but also infinitely many irrational points for the value 0. And moreover, we know the rational points lie dense in the real number line. Please remember, this is exactly how we constructed the real number line. For this reason, it's very hard to draw this graph of the function correctly because you have infinitely many jumps no matter how much you zoom in. And there you might already see that this function is not Riemann integrable. You see this when you want to choose a step function psi that lies above the graph of f. Such a step function then also lies essentially above 1. This is simply because for any segment you choose on the real number line, you always find a rational number. Hence, the value 1 is always included in such an interval. Indeed, the same holds for the irrational numbers when we want to choose a step function phi from below. There, the step function also has to lie essentially below 0. In summary, you see we have two properties here that hold for all step functions psi and phi. And therefore we have immediately an estimate for the two integrals here. And the conclusion will be we can't push the difference below 1. Of course, the first integral will always be greater or equal than 1 and the other one always less or equal than 0. In other words, we cannot fulfill this property for all epsilon. In fact, this is all we need in order to show that the Dirichlet function is not Riemann integrable. Here again, in the difference, this first part here is always greater or equal than 1, and the second part without the minus sign is always less or equal than 0. Hence the difference of both numbers is always greater or equal than 1. Okay, there you see, this was our first counterexample. Then next I would say we look at a function that is actually Riemann integrable. Of course, for the start, let's look at a very simple example. And I guess the identity f of x is equal to x is a very suitable example. This is simply because when we draw the graph, we immediately see what the integral should be. You see, the area is given by this triangle, which means the area should be 1/2. It's simply half of the square, where we have the sides as 1 and 1. However, if we work with the definition of the Riemann integral, what we need to, we can't use the triangle, we need to use rectangles. Hence, here we can actually see if our approximation works. Okay, now the question here is, what is a good step function we can choose here? Now, the one we see in the picture has 4 steps. The first height here is 0, then we go up 1/4, then the next quarter, the next quarter, and then it's the end. Hence, we have our 4 values, 0, 1/4, 2/4, and 3/4. Also, it's not hard to see that we split the x-axis also in 4 equal parts. So we have the interval 0 to 1/4, 1/4 to 2/4, and so on. Okay, so you see, this is a well-defined step function you can choose for the approximation from below. It has exactly 4 equidistant steps, therefore let's put a 4 into the index here. Of course, this tells you now that the approximation will get better when we choose similarly a step function with more steps. In fact, this is exactly what we will do, but now for an arbitrary integer n. Hence, we have exactly n steps now, which means the denominator here and here is now n. However, now instead of writing n different cases, I want to put all of them into one closed formula. And this is what we can do with another index k. So you should see, when k is equal to 1, we are in the first case. K is equal to 2 gives us the next case, and so on until k is equal to n gives us the last case here. Hence, the only thing missing here is now the value at the position, which is k minus 1. Which definitely fits because it's 0 in the first case, 1 in the second case, and so on. Okay, so this is a step function that looks like this, but now with n steps. Okay, maybe it's not so precise because here we should have chosen an open interval. However, then you see it will clash with the last case here. However, we can ignore all of that because you already know for the integral the boundary points here don't make any difference. Speaking of the integral, maybe let's immediately calculate the integral of phi n. Now, as we have learned before, the integral of a step function is always the sum of the areas of the rectangles. Please recall, we have n steps, therefore we have n rectangles. Honestly, the first one has area 0, so we could ignore it, but we can include it nevertheless. So now the area of one rectangle is simply the height times the width. And by construction, this is for all our rectangles 1 over n. Here you see we have 1 over n squared, which we can pull out of the sum. And then you see the only thing we have to calculate now is the sum of the first n minus 1 integers. And there we can use something some people call the little Gauss formula. In this case here, it's n times n minus 1 divided by 2. In the next step, you see we can simplify this into 1/2 minus 1 divided by 2n. Okay, so this is our result here, the result of this integral. And what you should immediately see is that if our approximation gets better and better, so if we send n to infinity, the result is 1/2. However, that's not enough for showing that f is Riemann integrable, because we also have to approximate the integral from above. And of course, this is now what we do with a similar step function psi. Here I would say, let's use the same picture as before to sketch the new step function. Of course, it should be the same staircase as before, but now shifted above the function. Therefore, the definition of psi n should look more or less the same as the definition of phi n. Of course, the partition of the x-axis should be the same, we only have to shift the values. Indeed, instead of k minus 1, we now can choose k. So you see, it's not hard at all to define such a step function. And indeed, in the same way as before, we can calculate the integral. Again, it's just a step function, so we add up all the areas of the rectangles. And now the only difference from before is that the height of the rectangles is slightly larger. Still, here we can pull the factor 1 over n squared out of the sum, and the only thing that remains is the sum of the first n numbers. This means that we can apply the same formula as before, but now we have one additional number at the end. For this reason, this sum is then given as n times n plus 1 divided by 2. Okay, and then in the last step we can simplify this again and we get 1/2 plus 1 over 2n. So with this, you should see we've reached our goal. Because the difference between these two integrals is exactly 1 divided by n. In other words, we can make the difference as small as we want. So if you recall the epsilon criterion from above, then you see that this function f is Riemann integrable. And of course, this is our result here. Moreover, we also get the value of the integral of f, which is 1/2. Of course, not a surprise for you, but now we have proven it. Okay, I think that's good enough for our first example here. We will consider more complicated examples later. Therefore, I hope that I see you in the next video when we continue with the Riemann integral. Have a nice day and bye!